Hey, look, a rainbow.
Yes, it's very beautiful. In fact, the legends of many cultures see the rainbow as a kind of bridge between heaven and earth.
Really? Well, that's an interesting idea.
But science has figured out the secret of rainbows. I can reproduce a rainbow for you using a triangular prism.
Oh, how does that happen?
Well, the same phenomenon takes place in both cases. Refraction of light. In this lesson, you will learn about dispersion and scattering of light. At the end of this lesson, you will be able to identify the general terms associated with a triangular glass prism, demonstrate refraction of light through a triangular glass prism, demonstrate the dispersion of white light by a glass prism, explain atmospheric refraction through twinkling of stars, apparent sunrise and sunset, explain through the concept of the scattering of light, the Tyndall effect, and reddening of the sun at sunrise and sunset.
You said you could show me a rainbow through a prism. What exactly is a prism? Is a triangular glass prism a special kind of a prism?
A triangular glass prism, to be specific, is a piece of glass that has 2 triangular and 3 rectangular faces. You may have studied how light refracts through a glass slab. You can think of a prism as a triangular piece of glass carved from a wide-bottom glass slab. Let's see how light refracts when the glass slab is converted to a prism. Consider ABCD, the cross-section of a glass slab of a certain thickness. A ray of light is incident on the face of the slab, represented by AB. This incident ray refracts through the path shown. After refraction through the 2 surfaces, the ray emerges from the face of the slab represented by DC. The surfaces of the slab represented by AB and CD are parallel. Hence, the emergent ray is parallel to the incident ray. We truncate the surface of the slab represented by CD, so that the cross-section now forms a trapezium as shown. As you can see, now the emergent ray is not parallel to the incident ray anymore. As we continue truncating the slab, the direction of the emergent ray keeps changing as shown. Finally, we get a shape with 3 rectangular surfaces and 2 triangular faces. We refer to this as a triangular prism.
Wow! I can see how the emergent ray is emerging at a different angle altogether now.
Yes, the shape of the prism impacts the way the incident ray refracts. The formation of a rainbow is a combined effect of refraction and another phenomenon called dispersion. Let's begin with refraction and review the general terms associated with the triangular glass prism. The rectangular faces in a triangular glass prism are known as refracting surfaces. The line along which the 2 refracting surfaces meet is known as the refracting edge of the prism. The angle between the 2 refracting surfaces, denoted by the capital letter A, is called the angle of the prism or the refracting angle. The base of the prism is the rectangular face of the prism that does not take part in refracting light. Consider XYZ, the cross-section of a triangular glass prism. When a light ray PQ is incident on the face XY of the prism, it refracts at the 2 refracting surfaces of this prism and follows the path PQRS as shown. Now, a quick recap of the terms associated with refraction. The ray of light that is incident on a surface is called an incident ray. Therefore, PQ is the incident ray. Q is the point of incidence. The ray that deviates at the point of incidence due to a change in the medium is the refracted ray. In this case, the refracted ray is the ray that travels inside the prism between the two refracting surfaces. Thus, QR is the refracted ray. The refracted ray again incidents on the other surface of the prism and then emerges from it into the air. This light ray emerging from the prism after refraction is called the emergent ray. Here, RS is the emergent ray. Normal is the imaginary line drawn perpendicular to the surface at the point of incidence. The angle formed between the incident ray and the normal at the point of incidence is known as the angle of incidence. Thus, here angle I1 is the angle of incidence on the face represented by XY. Similarly, angle R2 is the angle of incidence on the face represented by XZ. The angle between the normal and the refracted ray is known as the angle of refraction. In the absence of the glass prism, the incident light ray would follow the path PQ-OQ'. Due to the prism, the light ray emerges along the path ORS. Thus, the light ray deviates from its initial path. The angle between the directions of the incident ray and that of the emergent ray is called the angle of deviation and is represented by Greek letter delta or theta d or the English letter d. Here, angle Q-OR is the angle of deviation. When the light ray PQ incidents at Q on the face XY of the cross-section XYZ of the prism, it refracts and propagates forward inside the prism. As the light ray passes from a rarer medium, which is air, to a denser medium, which is glass, it bends towards the normal. When this refracted ray incidents on the other face of the prism XZ at R, it refracts again and becomes the emergent ray RS. Here, the light ray refracts from a denser medium, which is glass, to a rarer medium, which is air. Hence, the light ray bends away from the normal. Thus, a light ray refracts twice as it propagates through a triangular glass prism. The emergent ray always propagates towards the base of the prism.
Okay, that was half the picture. What about dispersion?
To understand dispersion, let's look at some videos of our annual day celebrations.
I remember the amazing lighting. I wonder how they got those effects.
Actually, prisms were used for those effects as well. That's where dispersion of light comes in. Light rays refracted through a prism disperse and give rise to very vibrant colors.
Where do these colors come from?
You'd be surprised to know that these are all constituents of white light. When a white light ray passes through a prism, it refracts and splits into its constituent colors in the process of refracting through the prism. The splitting of white light into its constituent colors is called dispersion of light. This is how you get the rainbow effect through the prism as well. Light disperses and creates a rainbow effect when it propagates and refracts in a prism. Let's conduct an experiment to see how we can create this rainbow effect through a prism. For this experiment, we take a prism on a horizontal surface as shown. On one side of the prism, we place a source of white light. Between the light source and the prism, we place a cardboard having a pinhole. This helps in producing a very narrow light beam through it, similar to that of a ray. Finally, on the other side of the prism, we place a white paper as shown to catch the dispersed emergent beams. This white paper acts as a screen. Can you see that strip of colors? Let's check out the order in which these colors appear from bottom to top. First is violet. Second is indigo. Next is blue. Then green, yellow, orange, and lastly red. The same colors as that in a rainbow, right?
Yes, I see what you mean by creating a rainbow through a prism now.
To Iranian Muslims, even the brilliance of the colors in a rainbow is significant. For example, prominent green means abundance, red means war, and yellow brings death. Note, the order of colors in a rainbow is popularly identified using the acronym VIBGR, each letter standing for a color in order. The same order of colors is visible in a rainbow.
But a rainbow has bands of colors.
Ah, don't worry. We can create bands too. Suppose you replace the cardboard having a small pinhole with a cardboard having a horizontal slit, that is, an extended light source. The vertical strip of colors you just saw expands to bring out bands of colors similar to a rainbow. There! Doesn't that look like a tiny rainbow?
So, it does.
Auditorium stages are also fitted with hidden rotating prisms that give exciting visual effects to support the performances on the stage. In stage lighting, several light beams are passed through rotating prisms to create spectacular effects.
But why do these colors get separated when passed through the prism?
When white light propagates through a prism, it refracts at an angle. However, the angle of refraction of each of constituent colors of light varies a little. This is because the frequency and hence the wavelength of each of the constituent colors of white light is different. This leads to a difference in the refractive index of the glass for each of the colors. The difference in refractive index leads to different angles of deviation for each of the colors when light is passed through the prism. This is how we obtain a band of different colors on the screen.
But there is no prism in the atmosphere. So where does the rainbow come from?
I was just coming to that. Let's now solve the mystery of the rainbow. As it happens, we do have something like prisms in nature. On a sunny day, when the rainfall has just stopped, some raindrops remain suspended in the air. These drops act like refracting media, like prisms, for the sunlight. When sunlight incidents on these raindrops, it gets refracted and disperses to reveal its constituent colors. Thus, you can explain the formation of a rainbow through the concept of the dispersion of light. The refraction of light leads to a number of other phenomena that you see daily. Remember the rhyme about the twinkling stars from your childhood?
Sure, I do.
Well, why do you think stars twinkle?
I'm not sure. I never really thought about it. Is refraction associated with twinkling of stars?
Definitely. The twinkling of stars can be explained through atmospheric refraction. Atmospheric refraction refers to the apparent random wavering or flickering of objects due to inconsistency in the physical conditions of the refracting media, such as air. In fact, atmospheric refraction can explain twinkling of stars as well as apparent sunrise and sunset. Let's first look at the twinkling of stars. Since our atmosphere is heterogeneous, that is, made up of many layers of various densities, the light reaching us from the sun or stars is refracted multiple times. As it crosses each medium, it refracts. Since these media or the layers of air are constantly moving, the angle of refraction of light is changing continuously. Therefore, we see the light from the stars flicker. In scientific terms, we refer to the twinkling of stars as astronomical scintillation.
That's very interesting. And what were you saying about apparent sunrise and sunset?
Well, not many of us realize this, but the fact is, we see the sunrise before the sun actually rises above the horizon. So, when we see the first rays of sunlight, we are actually witnessing an apparent sunrise. This happens because atmospheric refraction causes astronomical objects to appear higher in the sky than they really are. Similarly, sunset occurs shortly after the sun crosses the horizon.
How does this really happen?
When the sun is just below the horizon, its rays enter Earth's atmosphere and are refracted towards the Earth. The refracted rays reach us, making it appear as if the sun has already risen above the horizon. This is the apparent sunrise. The actual sunrise occurs when the sun actually crosses the horizon. Conversely, the apparent sunset occurs slightly later than the actual sunset. Since the light from the sun is already below the horizon, it refracts through the atmosphere, enabling us to see the apparent sunset even after the sun has already set. Now, another question for you. Can you tell me why the sky appears blue in color?
Well, that is the natural color of the sky, I guess.
If the natural color of sky is blue, then why does it appear red during sunrise and sunset?
I'm not sure. What's the reason behind it? Is it due to refraction of light as well?
Not quite. It's the result of scattering of light. Scattering of light is the deviation of light rays from its straight path. Almost all objects scatter light. That is, they reflect light rays incident on them. But some objects scatter light of some specific wavelengths, like the white ray of sunlight from the ventilator of your classroom or the golden hue in the forests. Light travels in a straight line as long as no object or particle obstructs its path. However, most media are heterogeneous, like our atmosphere, which is a mixture of gas molecules and other dust particles surrounding the Earth.
And as light propagates through the atmosphere, it travels in a straight path until it is obstructed by bits of dust or gas molecules, right?
You got it. Out of the 7 colors of light, blue has the shortest wavelength, and therefore experiences more scattering than other colors. Therefore, the sky appears blue to us.
Very interesting. Are there other examples that show the scattering of light?
Sure. Scattering of light gives rise to many amazing and spectacular phenomena such as Tyndall effect, reddening of the sun at sunrise and sunset.
What is the Tyndall effect?
The Tyndall effect is the scattering of light by colloidal particles. Observe this narrow beam of light when I pass it through this colloidal solution.
Wow! I can see the beam of light passing right through the solution.
Yes, that is the effect of the scattering of light. When the beam of light is scattered by the colloidal particles in the solution, its path is illuminated. This phenomenon of the scattering of light is called the Tyndall effect. The illuminated path of the beam is called the Tyndall beam.
Is it only in colloidal solutions that we see the Tyndall effect?
No. You can observe the same even in air laden with dust particles, like in a dusty room. The Tyndall effect can also be observed when a fine beam of light enters a room through a small hole, such as an aperture in a ventilator. This happens due to the scattering of light by particles of dust and smoke in the air. Similarly, when sunlight passes through the canopy of trees in a forest, you can see the Tyndall effect at work again. The mist in the forest contains tiny droplets of water which act as particles of colloid dispersed in air. In fact, here's an interesting incident related to the Tyndall effect. London, in the summer of 1815, frequently saw prolonged and brilliantly coloured sunsets and twilights. This was explained by the Tyndall scattering of sunlight by ash particles in the upper atmosphere. These ash particles were produced by the earlier eruption of the volcano Tambora. Now, look at this sunset. The sky has turned red.
Wow! What a lovely sight! You said that the red color of the sun at sunrise and sunset can also be explained through the scattering of light.
Yes, let me explain. As the sun begins to set, light must travel farther through the atmosphere before it gets to you. Therefore, more of the light is scattered. As less direct sunlight reaches you, the sun appears less bright. The color of the sun itself appears to change, first to orange and then to red. This is because the short wavelength blues and greens get scattered. Only the longer wavelengths are left in the direct light beam, which is what reaches your eyes. Therefore, you see longer wavelengths and the sky appears red, pink, or orange. Can you recall any application which you can relate to the scattering of light?
I think I have heard about the red color used in danger signals, but don't know whether it relates to the scattering of light.
Actually, that's a very good example. Red has a longer wavelength, and hence it is least scattered in any type of the atmospheric conditions. Due to this, the signal appears without change in color for longer distances. Therefore, it is effective to indicate the danger signal universally. This brings us to the end of this lesson on dispersion and the scattering of light. In this lesson, you have learned about refraction and dispersion of light through a triangular glass prism, formation of a rainbow, atmospheric refraction, and the scattering of light. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson.